So today, we're going to pull back the curtain on two invisible giants of technology. These are the hidden workhorses that make our entire modern world tick, and you probably use them thousands of times a day without even knowing it.
Think about it for a second. It really seems impossible, right? How do you possibly connect the colossal, raw power of the electrical grid with the delicate, microscopic world inside a computer chip? The difference in scale is it's mind-boggling. To figure out how this amazing trick is pulled off, we need to look at two key inventions. One of them tames electricity on a massive scale, and the other one directs it with pinpoint precision. So let's start with the big picture.
Okay, so the first huge challenge is just getting electricity from point A, the power plant, to point B, your town, without basically losing it all along the way.
Yeah, if you tried to send power straight from the station to your house at the voltage your outlets use, it'd be a disaster. The resistance in those long wires would just burn up a huge chunk of that energy as wasted heat. Super inefficient.
So the clever solution is to crank the voltage way up. We're talking hundreds of thousands of volts. This lets the same amount of power flow with way less current, and less current means you lose dramatically less energy to heat. But how in the world do you change voltage on that kind of scale?
The answer is this beautiful piece of engineering, the transformer. It's an elegantly simple device, really. It's just two coils of wire wrapped around a steel core, no moving parts, and by changing how many loops of wire are in each coil, it can step the voltage up or down using the magic of electromagnetic induction.
And this whole process is literally the backbone of our electrical grid. You've got a step-up transformer at the power plant that boosts the voltage so it can travel efficiently, and then a series of step-down transformers at substations and maybe on a pole on your street that bring it back down to a safe, usable level for your home.
All right, so the power has made it all the way to your wall socket. We're done, right? Well, not quite. There's another huge problem. The power is still in the wrong format for your delicate gadgets to actually use.
This is a really fundamental issue. The electricity coming out of your wall is constantly switching direction. That's what alternating current, or AC, is. But your phone, your laptop, pretty much all modern electronics, they need a steady one-way street of electricity. They need direct current, or DC.
And the hero of this part of the story is the diode. It's a tiny little electronic gatekeeper that does one simple but absolutely critical job.
Just picture AC power like a wave in the ocean, flowing forward for a bit, that's the positive part, and then flowing backward, that's the negative part, over and over again.
So what the diode does is it basically acts like a bouncer at a club. It lets all the positive current flow right through, but when the current tries to flow backward, in the negative direction, the diode just slams the door shut. No entry. It creates a one-way street.
Now, using just one diode gets us halfway there. But the power is still kind of bumpy and pulsating. So to fix this, engineers do something really clever. They use a few more components to capture all that power and smooth it out, giving us that clean, stable DC power our electronics need to survive.
But here's the thing. The story of this tiny, crucial component, it doesn't start in some high-tech lab. It starts with one of the most famous inventors in history who stumbled on the basic idea and completely missed what he had found.
So let's go back to the 1880s. Thomas Edison is trying to perfect his brand new light bulbs. And he notices this weird thing happening. A mysterious black soot is forming on the inside of the glass, but only on the positive side of the filament. He was fascinated, but he had no idea why it was happening.
What he had accidentally discovered was the world's very first diode, a one-way flow of current through a vacuum. He even patented it, called it the Edison effect. But he never figured out what it was good for. It actually took another inventor, John Fleming, more than 20 years to realize, hey, this is the perfect thing for detecting radio waves, and that discovery really kicked off the entire age of electronics.
Okay, so let's put it all together now. Let's bring our giant macro world and our tiny micro world together and see how these two components work as a perfect team.
So really, when you boil it all down, they solve two totally different but equally vital problems. The transformer is kind of like the gears of the system. It changes the power level up or down for whatever job is needed. And the diode, well, that's like a one-way valve, making absolutely sure the power only flows in the right direction.
And that's their perfect partnership right there. The transformer manages the sheer scale of the power, making it possible to move it across the country. Then the diode refines that power, making it safe and steady enough for the delicate circuits inside a chip. You gotta have both. Without them, our digital world just stops.
It's a pretty powerful reminder, isn't it? That sometimes the biggest revolutions don't come from the most complicated machines imaginable, but from finding an elegant new way to use a really simple, fundamental idea. Makes you wonder, what's the next one going to be?